Alright, so we just finished up the video about summations, and we talked about how n times n plus 1 divided by 2 really could be symbolized by this shape. This is n times n plus 1 divided by 2 as a way to very quickly figure out what 1 through some number is. And so I wanted to quickly take a moment and talk about how this relates to integration. And I won't get too much into this because I think it deserves more time, but just as a very quick reference for how this relates, I thought it might be useful. So let's imagine that this, instead of stopping at 4, right, we have 1 plus 2 plus 3 plus 4, went all the way up to 200, right? We would get a shape that we would need to zoom out from. And when we zoomed out from it, it would start to look a lot more triangular, right? It's kind of like if you're looking at a picture on like Microsoft Paint or something, and you look really closely, you can see the individual steps, but if you zoom out far enough, it starts to look kind of straight. It starts to look something like, this is the best representation I can do on using Legos, but it starts to look a little bit more triangular. And what's interesting about this is that if you get to a really big number, like, we'll say 1 billion, and you have one side of this shape that's 1 billion, and the other side is 1,000,000,001, it will be virtually indistinguishable from a square. Right here we can tell that this is a rectangle, and in fact, the smaller you get, the easier it is to see that it's a rectangle. I mean, that's even more of a rectangle than this shape is. Or, by the way, we could flip it around where that shape is. It's because proportionally just one different on this is, well, 1/5, whereas it'd be 1/3 on the other. And it'd be 1/1,000,000,000th, or I guess 1/1,000,000,000th and 1,000,000,001th, however you say that, on the huge shape. So that extra 1 would start to become so trivial as to really not even be important. You're trending towards basically saying, instead of n times n plus 1, when you have 1 billion, right? You could basically just call that, 1 billion squared. You could say 1 billion times 1,000,000,001, or 1,000,000,001, but 1 billion squared basically is what we need divided by 2. And the reason for that is because you're getting closer and closer, if you zoom out, to what just seems like a triangle. I mean, it really just looks like 1 billion times 1 billion at that point, divided by 2, which is where the integral for x comes from. Let's say we went from 1 to 1 billion. You could just solve that as, well, as 1/2 x squared, which is exactly why. It's because it's x squared. And by the way, it doesn't have to go to a big number. You could just say the intervals are less. So instead of being an interval of 1, like we're used to with summations, where it's going 1 to 2 to 3 to 4, what if it was 1/2? And then, so if it was like 1 plus 1.5 plus 2 plus 2.5, and so on. It would get to where, instead of being big steps, they were little tiny steps. And then such tiny steps that it just ended up looking like a triangle. And we're nearing that shape, which would just be x squared divided by 2. Which, if you looked at a graph, again, makes sense. If that's the graph, a pretty poor graph of x. And I wanted to figure out what the area under the curve was from 0 to 4, for example. Well, isn't that just, I know that this is 4. That's 4. That just makes basically 4 squared divided by 2. It's the area of a triangle. Base times height divided by 2. So that's kind of where summations lead into integration.